This is a question about magnetic flux linkage, and induced EMF. Let's read the question. A small solenoid of area of cross-section 1.6 times 10 to the power of -3, so this one is the smaller solenoid, is placed inside a larger solenoid of area cross-section 6.4 times 10 to the power of -3. So you can see that the area is 4 times bigger, right? 6.4 divided by 4.6 is 4 times. So if this is A, this is equal to 4A. Just casual observation. All right. The larger solenoid has 600 turns, and the smaller solenoid has 300 turns. So if 600 turns is N, then 3,000 turns, not 300, 3,000 turns will be 5N, because 5 times 6 is 30. Yeah. Okay. So compare the magnetic flux in the two solenoids. So what is important to know is that the magnetic flux can be calculated using the equation BA. All right. So we do have B. B is equal. So right here, B is equal, or is the same, since the small solenoid is inside the big solenoid. They sort of like share the same axis. Inside the larger solenoid. Okay, so which means the only thing that affects the flux is A. So which one has a larger area? Larger solenoid. So you don't really need to explain, you're just asked to compare. So I would say that the larger solenoid has a greater magnetic flux. Don't have to explain, but I'm explaining in a bracket since the cross-sectional area is greater. It's also in the name, right? Big solenoid, small solenoid. Okay. Compare the magnetic flux linkage. So magnetic flux linkage here, this phi, is actually NBA, National Basketball Association. Okay, so right now, if you look at this, if I want to calculate NBA, or my flux, this will be phi N, B is the same, this is A. So this is phi NBA. Of course, you can put the values in to calculate lah, but I am not that inclined because I can see the ratios are nice numbers. Okay, so this one will be N times B times 4A. So this is 4 NBA. So you can see that the flux linkage for the larger solenoid is less because there is less turns. Okay, so it's just the turns is 5 times less, although the area is 4 times more. So the effect of the turn is bigger. All right. Okay, you can always calculate like what I did. All right. So I'm going to put this one here. I'm going to say that the larger solenoid has less magnetic flux linkage. And if you want to explain, you can just bracket and say that the product of Na for larger solenoid is less. Okay, so larger solenoid has a greater magnetic flux, but less magnetic flux linkage. Of course, you can also write about the smaller solenoid. So if you want to make it more clear, but it's just 1 mark, so I want to write 1 sentence and move on if I'm a student now. But you can make it more clear by saying the larger solenoid has a greater magnetic flux than smaller solenoid, and the larger solenoid has less magnetic flux linkage than the smaller solenoid. So this is your basis of comparison. This is your compare. Compare the large solenoid to the small solenoid. All right, that's A and B. C part 1, state Lenz law of electromagnetic induction. So this is the opposition one, and it talks about the direction. Lenz law talks about direction. Faraday, where E is equal or proportional actually, where E is proportional to the flux, rate of change of magnetic flux. This one is Faraday, and it's about magnitude. So this one is about direction. So I'm going to start the definition with direction. Direction of our induced EMF is such as to oppose the change, right? So produce effects that oppose the change causing it. Okay, so the key word here is direction of induced EMF. Okay, it's such that it produces effect that oppose the change causing it. So there's always a change when you want to apply Faraday or Lenz law or look at electromagnetic induction. Okay, so the ability to see what the change is and to fight that change is what Lenz law is about. So direction of induced EMF is such as to produce effects that oppose the change causing it. Okay, so this kind of effect can look like can be seen, for example, like a magnetic force, either a force of attraction or repulsion, depending on the change. It can also be seen as a conversion or a loss in energy / work done by force. So the system that actually is creating the system that's actually creating the change is the one that loses energy. But let's look at the question, part 2. All right, so it says here that the terminal of the smaller solenoids are connected together, and the smaller solenoid is then removed from inside the larger solenoid. So let's look at the diagram again. So this is my diagram. Okay, the first thing I do is I connect the terminal of the smaller solenoid, aka I just form a connection here. Okay, so now the circuit is complete. Smaller solenoid is removed from inside the larger solenoid. So you can tell from my drawing, or rather I have actually pulled the solenoid out. Okay, meaning in order to pull this one out, I need an external force. I put this FEXT. With reference to magnetic field, explain why a force is needed. So if there is a force needed, it means that the larger solenoid is attracting the smaller solenoid. They say I need an external force, right? An external force is needed to remove the smaller solenoid, implying that the larger solenoid is reluctant, don't want the smaller solenoid to go, oppose the change. The change here is smaller solenoid is like, bye bye, I go away, and then the coil is like, no, come back. This is the magnetic force. So the larger, implying the larger solenoid is attracting the smaller solenoid. Okay, it's a bit like, I'm going away, says the smaller solenoid. No, come back, says the larger solenoid. Because we want to oppose the change, and the change here is the solenoid running away, the smaller solenoid running away. So the larger solenoid will try to pull it back. But of course, we can't write that as an explanation. That makes no sense. It sounds like a very nice Shakespearean drama. But I really need to see how it relates to Lenz law. Okay, because part 1 we define Lenz law. But step by step, as per usual, we are going to go through the template that I've mentioned just now. Number 1, we look at the change in flux. Okay, what causes the change in flux? Identify the change in flux. Where is it? Number 2, if there is a change in flux, that means there is induced EMF. Again, we should also outline where is the induced EMF. And if there is induced EMF, there is current flowing. Again, where is the current flowing? Of course, they can all sit in the same sentence, obviously. But the idea of these 3 points should be clearly seen, whether it's 3 different sentences or 1 sentence. Okay, and finally, we have to try to use this to answer the question. Okay, that there is attractive force between the larger and the smaller solenoid. So from current flow going to FB attracting the small solenoid. Okay, so we're going to first write down the first three parts first. Okay, so number one, I can say that there is a change in magnetic flux. So identify the source of the change. As the smaller solenoid is removed, there is a change in magnetic flux linkage in the smaller solenoid, inducing an EMF. So you just mention all in one sentence also can. As the smaller solenoid is removed, there is a change in magnetic flux in the smaller solenoid, inducing an EMF. Good enough. Okay, number two. Due to the induced EMF, okay, there is now induced current in the smaller solenoid. Because there is EMF, so there's current flow. Okay, but what happens when there's current flow? Part of the outcome of the current flow, if you want magnetic force, is that you will have a magnetic field. So there is induced current in the smaller solenoid. Then we can continue and say that this causing a magnetic field around it. So there is now a magnetic field in the smaller solenoid. Number three. Interaction between the magnetic fields, because now you got two magnetic fields of the larger solenoid and the smaller solenoid. So we got the interaction between two fields creates an attractive magnetic force between them, and hence an external force is required, which you can write or you don't write, is also okay. All right, so the second mark is when you say there is induced current in the smaller solenoid and then there is a magnetic field around it. This one is P1, this one is P1. Okay, and very important, interaction between the two magnetic field of the larger solenoid and the smaller solenoid causes an attractive magnetic force. Okay, so because now there's an attractive magnetic force between the solenoids, hence an external force is needed. To remove the smaller solenoid. The last part is just to round up the question. You don't have to write it if you don't want to. Okay? So in conclusion, when you write explanation like this, your starting point tend to look like the same. Always identify the change in magnetic flux and where does it occur in the smaller solenoid. Okay, the changing magnetic flux occurs in the smaller solenoid. Okay, and this induces an EMF. So always identify the change in flux. Where does it happen? Induce EMF, where? Okay, and then the second thing to note is that there is now induced current if the loop is complete. Okay, so because of this induced current, there's a magnetic field. So current flow, and because current flow, there's magnetic field. So the magnetic field of the small coil interact with the magnetic field of the large coil, and then that creates a magnetic force. Okay, it's a bit like north pole attract north pole. North pole attract south pole attract north pole. Okay, so and because of this, the force is needed to remove the smaller solenoid. Of course, in this case, the question is slightly easy because it actually tells you there is an attractive force. It tells you indirectly because it says a force is needed to remove the smaller solenoid, implying the larger solenoid is actually attracting the smaller solenoid. That's why you need an extra force to pull it out. But what if you don't know? What if you don't know? Well, there are a few ways to actually be very sure about this. Number one, when we look at this, larger solenoid is attracting the smaller solenoid. This one is preventing it from leaving, aka oppose the change causing it. And the change was the solenoid wants to leave, and you oppose that leaving by attracting the solenoid back. Okay, so you oppose the change. That's one way to look at it. The second way, which is the more long-winded way, is actually to try to figure out what is the direction of the induced field. So in this case, it's pretty much impossible to tell. By the way, the question is over, but I'm just going to do a bit of an extension discussion. It's pretty much impossible to tell the direction of the magnetic field in this coil, given the fact that we actually do not have the polarity of your DC power supply, aka I don't know whether this is positive, negative, or whether this is negative, positive. Okay, so for the sake of discussion, let's say this is positive and negative. Okay, just for the sake of discussion, and the current is going to go inside here, turn to the back, and then let's say come up to the front. Actually, we don't know. In fact, the drawing of this coil is quite bad. So maybe let me modify it a bit. Okay, I've modified it a bit by inserting sort of like a transparent looking tube to wind this around. But the whole point about the current is that it's going to go to the back and come to the front, and then flow down to the back here, which you cannot see. Okay, so go to the back here and come back up to the front. So the important thing here is the current is actually flowing up. But again, I don't know how the solenoid is wound. For all you know, the current could be flowing down, which means it comes to the front and then circle to the back. So it really depends on which one I draw dotted line. And right now, I draw the dotted line to the one at the back, okay? So I'm going to use my right-hand grip rule, okay? And I can determine that the direction of this magnetic field will be like so. Right-hand grip, thumb is here, field is going up. Okay, go to the back. So that is a current flow to the back, come back to the front. That's why the front is all pointing up. All right, let me delete that and let's go back to here. So this is the direction of your magnetic field. Direction of B is here. Okay, using your right-hand grip rule. This is B. Which means this is your north pole, north, and this is your south pole for the larger solenoid. Okay, so let me switch here. B. And now we are going to remove the smaller solenoid. So whenever we remove the smaller solenoid, there are some changes that happen in the smaller solenoid. So if we look at this, right now, the solenoid in this position also got magnetic field in this direction. This is the field of the large solenoid. However, when we move the coil, let me connect this. When we move the coil in this direction, what will happen is that the coil now suffers a loss. There's still magnetic field, but the magnetic field less already. So this B actually decrease. And then the small coil will panic. Hey, the field that I had is gone. I want to try to recreate that field. So I recreate the field in the same direction, B. So this B here is for the small solenoid. Okay? It is induced to oppose this drop in magnetic field. So we try to increase back in the same direction. But objectively speaking, if I now have two coils like so, I kind of have two magnetic fields. The large one was originally in this direction. All right? And the small one, because suffers a decrease in this large field because it is moving further away, panics, and from Lenz law, try to recreate the field that was lost. B. This is B in the small solenoid. This is B in the large solenoid. So these two fields will interact. It is the interaction between these two that causes magnetic force. Okay, causes a force. How does a force occur? Well, if you think about this, this is north pole, this is south pole of your large coil. Then this small coil inside here, here is south and then here is north. So can you not see that these two will attract attractive magnetic force? Okay, so it is totally not needed. You will understand that when I want to pull this coil away, the large coil is going to try to stop it by trying to attract this back, as well as an attractive force in this direction, FB. Okay? Or you can try to use the magnetic field. Large magnetic field inside the small coil becomes less solenoid. First it's right in the middle, now it's only the first half. The small coil will try to recreate the field that was lost, making this green field. This green field is due to induced current. It's from the induced current. Okay, so when we create this smaller field, okay, this smaller field is actually south pole here, and then you interact with the north pole from the large field, and then they will attract. Okay, but if we go back to the explanation, you don't really need any of those. What you actually need is just to explain the presence of the EMF due to the change in flux, first mark. Explain why there's a magnetic field in the smaller solenoid, second mark. Highlight that the interaction between two magnetic fields creates an attractive force. Now, interaction between these two fields creates an attractive force. That's it for this question. Okay, induction is a bit complicated, but it's something that you can actually understand by following a step-by-step analysis. Think of the change, where does it happen, where is the EMF, what's the consequence. All right, so I suggest you try more questions. Okay, every single induction question, the flavor is a bit different, but with practice, I'm sure you can get it. All right, induce your curiosity. I'll see you in the next video. Bye.